Good day! I'm Dr. T. Welcome to my office, and I'd like to jump in and talk a little bit about Cytochrome p450s. This is a family of enzymes, not a single enzyme, not some isozymes, but actually different enzymes that are all very similar, enough that we've classified them together, but they do have different preferences for their substrates, essentially. These enzymes are going to have a similar task. They're usually found in the liver, and their goal is to add alcohol groups and do general oxidation on what's called xenobiotics. Xenobiotics are going to be those things that are not natively found within the organism. So of course this would be things like pharmaceuticals, toxins, just random chemicals floating around in your bloodstream. Their goal is to add some alcohol groups to them and make them more hydrophilic. This way your kidneys can process them and number one down the toilet. Now, where does this become particularly interesting for us? Well, your pharmaceuticals are going to be xenobiotics. They're not typically stuff that are normally floating around your body anyways, and thus don't have their own dedicated pathways. If we talk something like glucose, it's got its own pathway to process. Now, once you consume a pharmaceutical, then it's going to be bouncing around your body, probably going to make its way to the liver, and part of your liver's approach to get it to a point where it can get rid of it, because once again, your liver's like, I don't know what this is, it's probably bad, let's get rid of it. Part of the approach is going to be start reacting with the Cytochrome p450. Now, different xenobiotics fit in with different Cytochrome p450s differently. So typically, each pharmaceutical is going to be processed mostly by one particular Cytochrome p450. This actually has some really interesting implications for us. For starters, these are different enzymes. You can have mutations. So you may have the wild type version, or you may have one of many different mutations. Those mutations may cause that particular enzyme to be more effective or less effective. This is one of the reasons why the amount of a certain pharmaceutical does not always produce the same effect. Let's say I take a pill. It dissolves, it goes in my bloodstream, it bounces around, it has its effect, but once it starts building up in my bloodstream, my liver's in the process of getting rid of it, modifying it, so then hopefully for the liver's term, not necessarily hopefully for me, presumably I took it for a reason, but probably inactivating it, although sometimes the liver's modification activates it, and then the kidneys number one down the toilet. Well, if my Cytochrome p450 that is processing that particular pharmaceutical in that pill is working more aggressively, then when I take it, it flushes out of my body quicker, and thus the amount that I need to take is actually higher. Alternatively, if that particular p450 is working slower, because it just happens to be a slightly different mutant that doesn't work as fast, then the same dose that a person with the wild type p450 would take might actually be an overdose for me. This is a common problem for things such as anesthetics, where you don't really want to go nuts with those things. Another interesting area of conflict with this one ends up being if I take two different pharmaceuticals at once, drug interactions. One way that these can interact is by them both, just by coincidence, being processed by one of the Cytochrome p450s. So in this case, this enzyme now has two pharmaceuticals it has to process. They're each effectively a competitive inhibitor to the other one. Your liver's like, I'll get to it when I get to it, but you just double loaded my work. As such, because the liver is now doing double duty, both pharmaceuticals are going to float around your body for longer, therefore strengthening both of them. This is one of the common reasons why pharmacists will warn about consuming grapefruit. Some of the molecules within grapefruit happens to be processed by one particular Cytochrome p450 that's important for a lot of other pharmaceuticals, and thus will make them particularly stronger. Now, I have been speaking about Cytochrome p450 as if the more it works, the faster you clear the drugs, and the slower it works, the slower you clear the drugs, and therefore the effective dose is higher. That's actually not always the case. Sometimes it's reversed, because sometimes the chemical you consume is not actually the drug in question. Sometimes it's what we call a prodrug. When you consume a prodrug, then the drug or the chemical you consume does not have a particularly important biological effect. However, once your liver starts processing that particular drug, it will change the prodrug into the actual drug. For this reason, if my liver is more aggressive at processing a particular drug, then I'm actually going to get more of it, or more of a spike. And therefore, my normal dose will actually be an overdose. Likewise, if my liver is slower at processing a particular drug, then, once again, my normal dose will actually be less of a dose because if that particular drug is a prodrug when I consume it. So things can flip-flop. This actually leads to a couple of important features that we are starting to incorporate into medicine. If you go back really kind of when computer databases became a thing, there was a big push for you to, kind of use the one pharmacy. And this was because they had a database of what pharmaceuticals you were taking. And in that database would be a whole list of this and that don't mix. And this would be because they would potentially be sharing a Cytochrome p450 or other enzymes in their metabolistic pathway. So I don't want to imply that Cytochrome p450 is the entire story. It is just a dominant part of the story. This way, if you were to have a doctor who would order both pharmaceuticals, the computer at your pharmacy would go, pick it again, try again, not doing this. And thus, you would catch drug-drug interactions. Now we're taking this to the next level with pharmacogenetics, figuring out which mutations of which Cytochrome p450s, as well as other enzymes involved in the metabolisms of pharmaceuticals you have, and thus knowing that, hey, you have the wild type, go like normal, or hey, you have this particular mutation, you need to adjust the dose or don't prescribe this particular drug. It's going to have what would effectively be drug interactions, but there's no actual drug it's interacting with. It's your genome. So with that said, Cytochrome p450 is definitely an interesting molecule, one that I have been fascinated for years with. So with that said, have a wonderful day.